Just a minute. Okay. So today is the first class of the subject formal language and automata theory. Uh, we have to cover a lot of things in this subject, but at the very beginning, it is always necessary to understand the idea and reason behind the evolution of this subject. So we will start. We will not dive into the subject directly. Rather, I am planning that we will start with a practical situation, like we'll start with a question that what is the basic way of communication between us. Now why this question arises in this subject, that is may not be clear right now. It will be clear day by day after this class. So if someone asks you that what is the basic way of communication between us, you will say that, oh, answer is very easy, it is some language. The language can be Hindi, can be English, can be Bengali, can be anything. Now, for example, if we consider English language, we know that English language contains a lot of letters. Now, putting these letters in a random way doesn't make any sense in the language. For example, if I say that ABCD, it doesn't make any sense. But if I say that how are you, I am fine, welcome to this place, sit down, and this type of small sentences, which is actually string combination of some uh, the letters, it makes some particular meaning. So that means, and one more thing is that if I say that how is you, you will say that this particular sentence is wrong. As an English sentence, this particular sentence is wrong. Where it is wrong? Instead of is, it should be are. So that means if you consider a particular language, not only putting the characters randomly or in a particular way is important. It is also important to follow some set of rules. And technically, we say this rule as what we call grammar. And if you watch it carefully, you will see that each and every language has some associated grammar with it, and they are not same. English language has its own grammar, Bengali language has its own grammar, Hindi has its own grammar, and all. So naturally we have to follow these rules to create a proper English sentence, or you can say string, from the computer science point of view. So this is all about a very practical scenario of any language. Now I want to extend this concept a little bit. If I say that we have a lot of different high level language in our computer science field, for example C, C++, Java and all, and we say they are high level languages, forget about the high level word, they are language. So if C is a language, then C language must have some associated grammar, as English have, English, Hindi, Bengali have. In the same way, the C Java must have some grammar associated with it. Now this particular language is not used by us, something like as a the human being. Instead of that, the difference between Bengali, English, Hindi and C, Java, C++ is that the first three languages are used by human being and last three language are used by machine. And what is a machine? Or specifically you can say computer. So what is a computer? Computer is, at least one thing I can say, that computer is an electronic device which follows some mathematical formulation. As simple as that. So that means each and everything that we run in a computer is somehow mathematically understandable by the computer, because computer follows mathematical formulation for each and every operations. So that means the language that we are dealing with, the high level languages like C, Java and all, must have some mathematical basis so that the computer can understand it. If I extend it a little bit, I can also say that the grammar that is associated with these languages must have some mathematical basis so that the computer can understand. So we will start understanding the idea of this subject from this question, that what is the mathematical definition of a grammar. So this mathematical definition, realize it we will start realizing it from an example. So let's take an example. So to understand this mathematical definition, just for time being, you forget about this automata theory and all. Just assume that you have a sentence like the boy eat an apple, a very simple English sentence. And now question is that this sentence is, the word sentence is just you consider that as an entity. And what I want to break this entity into several components such that each and every component point each and every word of this sentence. Let's make it a little bit clear that if I want to start from this word entity sentence, as a whole I can say that the boy eat an apple is sentence. Now how I can break this sentence into several components, smaller components. Actually you can say smallest level of components. I can say that by the nature of English language, I can divide the sentence into two parts. One we call, the first one is noun phrase 1, which is followed by a verb phrase. A very simple division I have done. Now why I'm dividing it, that we will realize it very soon. But here the division doesn't end. I can extend it more, each and every entity, this noun phrase 1 and verb phrase 1, into several other smaller components till I will not able to derive this sentence, the boy eat an apple. That means each and every smaller components will be able to derive the words individually. That is what I want. And that is why I started, suppose, from this particular root sentence, this one. I started from here. And this has been divided into two parts. And now I can extend it more, this noun phrase 1 as two part, which is an article and a noun one. Now why I am saying it is one, because you will find that in this verb phrase side we have another noun phrase, because I can consider this verb phrase as something like this. I can say by the nature of English language that a verb phrase can be rewritten as a verb followed by a noun phrase. Now since I have a noun phrase here already, that's why this one I have given as 1 and this one I have given as 2. Now still I cannot derive each and every word individually from these 4 leaf nodes of this tree. So I have to go little bit more. What I can do? I can say that this noun phrase can be again rewritten as an article followed by another noun. That's why I have given it a noun too. Now I can derive these 5 words of this sentence with this 5 leaf node of this tree directly, and I can say that this article maps with this particular word the, then noun 1 will follow this boy, then verb will derive this particular word eat, and second article I have this the, and the second noun that I have is apple. So you see, it was my intention that to derive this particular sentence from this sentence entity, a single entity. To do this, you see, I have divided the entity sentence into many parts and so on in different depths. So this particular tree structure I can consider as something like a rule in a form that a sentence can be rewritten as a noun phrase 1 followed by a verb phrase. This is rule number 1. Rule number 2 can be a noun phrase 1 can be rewritten as article followed by noun 1. This is rule number 2. Similarly, rule number 3 can be a verb phrase can be rewritten as a verb followed by noun phrase 2. Rule number 4 can be something like noun phrase 2 can be rewritten as article followed by noun 2. And some more rules is required, because if you consider only the rules that we have just defined, doesn't make this word till now, this sentence till now. To derive this sentence, we have to apply some more rules. For example, article can be rewritten as this the. Noun 1 can be rewritten as boy. Verb can be rewritten as eat. Article can be rewritten as the, and noun 2 can be rewritten as apple. If you don't include these last 5 rules, then it is not possible to derive this sentence, which is my intention. So that means if you start from a start symbol, for example, here the start symbol is sentence. Obviously, we don't write sentence every time. We put them with some specific letter. For example, I can say it at S. It can be N1, so or NP1. It can be VP, something like this. So just like a variable, then you can assume. So that actually signify this each and every nodes in this tree. So to derive this particular sentence, not only these rules are important, but also this article to the, noun 1 derives to boy, verb to eat, and all these are also important. So basically I can write them as something like this, that a sentence can be rewritten as noun phrase 1 followed by verb phrase. I have given in a just in a angular bracket just because we consider that these are not something which exactly I want to derive, because ultimately we want to derive these words, right? Now, among this particular rule or in this particular tree, we have various words, you can see, right? In this particular rule, VP, NP1, NP2, A, N1, V, N2, apple, eat, many things. And what is my goal? My goal is to derive these particular words in the sentence. So what we can see, that we have this set of rules in a, suppose somewhere placed, and using this set of rules in some particular order, I can generate this particular sentence, right? So now how this A, N1, V, NP2 are differentiated with this the, boy, eat, apple, all these words? We can say that these are actually what we call non-terminals. If you just relate this set of non-terminals with respect to this tree structure, you will see that all the non-leaf nodes are basically the non-terminals. You see, up to article noun 1, verb, article noun 2, up to this side, we have the non-terminals. And what are the terminals? The terminals are the words that exactly I want to derive. So that means the leaf nodes are actually what we call the terminals in the rule. And we say this type of, all this type of rules as the production rule. So we have a number of production rule over here, and using this production rule in some particular order, I can generate this particular sentence. For it, or in a language of computer science, you can say that using this set of production rules in some particular order, you can generate a particular string. So that means, and what is this? This string is within English language. It's the correct string of an English language. Now the mathematical definition of language I am coming later. But before that, one thing I can say, that these rules are, I mean, these are actually those uh, set of rules applying which I can generate the string of English language. That language, that the string can be the boy eat an apple, the string can be anything else. Now since this particular example is a very trivial example, that is why maybe you will not able to create more than one sentence with respect to this particular rule. But the idea of generating any string of English language is same in this way. So that means if you closely try to realize that what are the basic components that we have used to derive the string of this English language, that components actually as a whole signify the mathematical definition of grammar. For example, if you want to derive this particular sentence, you have to start from some non-terminal. Some non-terminal. That can be S, can be NP1, can be VP, can be NP2. One of the non-terminal. And that is what we call start symbol. So here this S is what we call start symbol. Why start symbol? Because I have started deriving this particular sentence, I mean this particular sentence from this S. And always remember, the start symbol is always same for deriving any string of the language. Now, without using this set of production rule, it is not possible to derive the string. That means there is one more entity, one more component that we have in the whole system is set of production rules. So that means not only this, we have a set of terminals also, which actually uh, deals, finds the string that we are trying to derive. So in this way, if we search about the exact mathematical definition of a grammar, we can say that a grammar can be defined using these four tuples: V, T, P, and S. What is V? V is the set of non-terminal symbols that we have seen. T is that set of terminal symbol, ultimately which one we are going to derive in some particular order. As an example, we have defined here that the boy eat an apple, but it can be, a sentence can be something like A B C A D C B A, something like this. If I consider, if I am able to somehow put some meaning of this particular sentence A B C D B C A, then it is correct in this English language. For example, we say, as just maybe a couple of minutes ago we were discussing that how is you is wrong with respect to English language. Yes, it is wrong. Why it is wrong? Because in the grammar it is defined as after how, before, when you will use you should use are. But if I design my own language, and over there if I define the grammar such that I will have is before this you, then in that particular new language, how is you will be the correct sentence and how are you will be the wrong. So it's totally a perception. That means the perception depends upon this grammar. How you are defining your grammar, that will actually change the language. So anyway, so let's proceed. We have this P also, which is set of production rule, because without this set of production rule in some order, we cannot proceed. We cannot derive the sentence or the string. And obviously, I have to start from some particular point. That is what we call start symbol, just what we have seen in the previous slide. So without one of these four components, you cannot define a grammar. You see? Because ultimately the purpose of grammar is to generate some language. If there is no grammar, it's not possible to have a language without any grammar. Nobody can say that there is a language L which doesn't have any grammar. It has to be. Because that is the basic, backbone of generating that language. And since we are dealing with computer language, which is actually follows some mathematical formulation, that is why it is necessary to realize that what should be the mathematical definition of a grammar. And that's why we can say that, okay, a grammar can be defined in this using these four tuples.